All right, everyone. Here is our first recorded lesson. If this is weird for you, it's equally as weird for me. So what we're going to be looking at today is we're going to be looking at types of bonds. So what we need to remember when we're dealing with the different types of bonds of ionic versus covalent is we're dealing with intramolecular forces. So the force of attraction between atoms that make up a compound, and not the force of attraction between two different molecules or two different compounds. The way that these bonds are formed is through differences in their electronegativity. So when we were looking at electronegativity before in our atomic theory, that was looking at the ability of an atom to accept a valence electron. So our nonmetals are going to have very high electronegativities, whereas our metals are going to have very low electronegativities. Looking at the difference in the electronegativities of the two atoms can help us determine what type of bond is being created between those two atoms. So what I'd like you to think about right now is what or when two hydrogen atoms approach each other, what forces are present. So on your own, I'd like you to brainstorm some of your own ideas of what might be some different forces that are present when two different hydrogen atoms come close together. So pause the video right now and answer that. So as I was saying earlier, this is some review. Electronegativity, it's the atom's ability to attract electrons, and that's attracting them to their valence shell. So if we're looking at our fluorine here, he is got some cookies, and he's attracting the electron closer to it by having those cookies. As a side note, of course, the fluorine atom would not have cookies. That's just ridiculous. If we look at our periodic trend of electronegativity, we can see that we've got our lowest electronegativity down here in our large metals, whereas our highest electronegativity is with our small nonmetals. And we have the general trend of increase like that in our electronegativity. So we know that our nonmetals have higher electronegativity versus our metals. Of course, review from our atomic theory unit. So what happens when two atoms of the same element form a bond? So if we're looking again at our hydrogen A and our hydrogen B, and we've got our two electrons, they're going to be fighting over who is going to be more attractive, right? We've got two of the exact same atom that have the exact same electronegativity. So where are those electrons going to be spending a majority of their time? And that's what we're going to be looking at now, of what different bonds can form. Here's a chart that shows the difference in electronegativity and then the ionic character. As our percent ionic character increases, that increases the likelihood that an ionic bond is going to be forming. So you can see that pretty much everything that is over a difference of 1.7 is increasing its ionic character by more than 50%. So we've gone from 51% with a difference of 1.7 all the way up to a difference of 3.2, which is very large, and now we have a 95% ionic character, meaning that 90% of that bond is showing an ionic character. With our covalent bonds, so a covalent bond is between two nonmetals, and the difference in their electronegativity is less than or equal to 0.2. If the difference in the electronegativities of the two atoms are less than or equal to 0.2, you are always going to have a covalent bond. This is meaning that we have an equal sharing of electrons. So the electrons are not spending more time around one atom versus the other. And the pair of electrons is simultaneously moving between the two nuclei. So the two atoms are equally sharing those electrons, which means that they have full outer shells. Our valence shells are full and happy. So if we look at our first example in the notes of hydrogen gas, we're dealing with two of the exact same atom, being hydrogen. So as we all know, we have how many valence electrons in hydrogen? That's right, 1. So they both are going to have a full happy shell when they come together and form that covalent bond as they're sharing those two different electrons. So the fact that they're sharing, we have one bond, which can be shown like that. We have a single bond. What do you think the difference in the electronegativity might be between these two atoms? They both have an electronegativity of 2.1, so our difference is going to be 0, which means we have a covalent bond. If we look at oxygen gas, another diatomic molecule, we've got our two oxygens, they come together, they're now sharing 4 electrons, okay? So if we're sharing these 4 electrons, we have 2 bonds, which means we have a double bond. So unlike hydrogen, which was a single bond, which was shown as a single line, when you have a double bond, you show it with 2 lines. Difference in our electronegativity again, each have a electronegativity of 3.5, which means our difference is 0. So how many electrons will be shared in a triple bond? Well, we already know in a single bond we have 2 electrons being shared. In a double bond we have 4 electrons being shared. And as you are all geniuses, I see that I'm sure that you can figure out the pattern here that in a triple bond we're going to be sharing 6 electrons. So what happens now when we have 2 different atoms forming a bond? So now we've got hydrogen and chlorine coming together. We've got an electronegativity in hydrogen of 2.1, an electronegativity of chlorine of 3.0. So which one do you think the electrons are going to want to spend more time around between hydrogen and chlorine? Well, chlorine is more attractive. It's got a higher electronegativity, meaning it's going to attract electrons better than hydrogen. So our electrons are going to be spending more time around that atom as opposed to the hydrogen. Now that we have some electrons spending more time around a different atom than the other within a compound, we have something new being formed. And what we have formed now is a polar covalent bond. So this is where we have now a difference in electronegativity of 0.3 to 1.6. So there's an unequal sharing of electrons, which is saying that electrons are spending more time around one atom than the other. If there's an unequal sharing of the electrons, meaning they're attracted to one atom more than the other, that results in a dipole. And we're going to get into that in a little bit more detail as we move on here. So let's look at hydrogen and chlorine. So we've got our hydrogen that's got 1 valence electron to donate, and we have chlorine that's going to be accepting 1 valence electron. Meaning our hydrogen becomes partially positive and our chlorine is becoming partially negative. So what do you think that means when it's partially positive and partially negative? I want you to think about that for a second. So what that's saying is that we are not positive and we're not negative because we have a compound that's formed that's happy and stable. If we had a fully positive section of fully negative, that means that this would still want to react. What we're saying is that they're only slightly positive and slightly negative, and that is meaning that the electrons are spending more of their time around chlorine than they are around hydrogen. This can be shown as our slight positive and slight symbol, or you can also show it with the arrow where this is denoting our positive end and the end of the arrow is denoting our negative end. And we have a difference of electronegativity of 3.0 being our chlorine, 2.1 being hydrogen, so we have a difference of 0.9. So we have that difference of between 0.3 and 1.6, meaning that this is a polar covalent bond. If we look at water, So when we're dealing with water, we have the hydrogens becoming partially positive and the oxygen becoming partially negative because the oxygen has a greater electronegativity than our two hydrogens. So we have a difference of 1.24, which is between our 0.3 and 1.6, making this a polar covalent bond. Another way that you can show this is here we're showing the slight positive and slight negative around the individual atoms. You can also show the partial charge of the entire molecule like that. So we have our slight negative region around our hydrogens and our slight positive region around our hydrogens and our slight negative region around oxygen. So what happens when we have two atoms coming together that have a very different electronegativities? Well, that's where we have an ionic bond. So if we look back at our periodic table, our first column is always going to have a +1 charge, second +2. We've got our transition metals that can be +2, +3, +4. And then over in our nonmetals with group 6 being -2 and our group 7 being -1. In an ionic bond, the difference is always greater than 1.6, meaning that there is a strong attraction of those two atoms together because there is a transfer of electrons, whereas in a covalent compound, there's a sharing of electrons. So in our ionic bonds, okay, it's between a metal and a nonmetal, as we already know. And they have an electronegativity difference greater than 1.6. There's no sharing. There's no sharing going on. There's only a transfer. And since those electrons have been transferred, that's what's creating the very strong difference in electronegativity. So we've got our metal atom being our cation or our positive ion. And we've got our non-metal being our anion or our negative ion. So what these are held together by is a electrostatic charge, meaning the positive is attracted to the negative. And that's what's keeping them together. Unlike in a covalent compound where they're sharing, that's what keeps them together. So we're looking at sodium fluoride. Sodium does not have a full valence shell. It wants to get rid of that one valence electron. Fluorine wants to accept one valence electron. There's not going to be any sharing because of the difference in electronegativities. There's now going to be an actual stealing of that valence electron to fluorine because it has such a large electrostatic difference. We then show this as a positive charge around our sodium, a negative charge around our fluorine, and we show that the difference is 3.1. So that electrostatic difference is causing these two to come together and form a compound, being an ionic compound. If at any point you need to go back through the video to review anything, go for it. In this, we've covered the different types of bonds, covalent bonds, polar covalent, which is a new topic, as well as ionic bonds. I hope this helps. See ya.